we have GA. General ability has so many. That's like a core subject.
Maybe. All right, let's start module 8 of this last module of the year 12. Congrats, just one more modules and the trials and the HSC and you're gone. Yeah. You know, think positive, just one more module. Out of 8, the last module, final goal.
Sure.
Okay, I'll tell you what's in the module 8 briefly, and then we're going to move on to chapter 1. So in the module 8, we're going to learn about some identification and analysis of the either inorganic compound or the organic compound here, okay? And these could be, either of these could be both qualitative and the quantitative. And this is all about the module 8. So you're going to learn about analysis of the qualitative analysis of the inorganic compounds, quantitative analysis of inorganic compounds, qualitative analysis, quantitative analysis of organic compounds. Jian, what was the organic compounds which we learned in module 7? Something with the carbon. So this is the organic compound means dealing with the carbons. So simply, inorganic compound is something that not using carbon. Okay, something that not carbons. For example, we're going to learn about these metals and non-metals. Mina, do you remember like when metals become ionized, what type of the ion could be? When metal becomes ion, would it becomes the positively charged ion, negatively charged ion? Or the cation, anion? Metals?
The metals become positive.
Positive. So metals becomes to cation, non-metals becomes to anion. Been a while. So in the first chapter, the chapter 1, we're going to learn about how do we qualitatively analyze the metals and non-metals. Make sense? It's kind of giving, and in second chapter, we're going to learn about how quantitatively we analyze the metals and non-metals. Lucy, what does it mean by the qualitative analysis or qualitative? What type of compound it is? Okay, types. So qualitative means about the types or the presence. So it's either be like a yes or no question. It's very simple questions like this. So it's like, hey, we have a calcium. Do we have a calcium here or not? Do we have the sulfate or not? Do we have a chloride or not? Types and presence. Quantitative is more about, hey, how much do we have in quantity? So you will be asked to using the titrations. For the quantitative, you'll be asked to find some exact number of moles, concentration, grams, sometimes the volumes, depends. Okay, that's what we're going to do in the chapter 2. For organic compounds part, we did a bit of qualitative, so we're going to talk about it a bit later. Okay, the questions and HSC, yes, we get both of the qualitative, quantitative, at least one question from here or here, combination of this, at least 1 or 2 questions from this two as well. Very important. So make sure you study every week to memorize the stuff I ask you to, because like, every week you've got a bunch of the things to memorize. All right, let's start from chapter 1 then. Qualitative analysis of the inorganic substances. Okay. All right. Okay, let's think about some chemicals we're living in, okay? All right, have you heard about something called the heavy metals? Okay. heavy metals, like something metals that are heavy. Why do we call the metals metals as heavy? Like, think about it in terms of heavy metals. What can you give me an example of heavy metals? It could be a lead, for example, lead. Assume that you're consuming some lead. Assuming that you're consuming some lead, or the mercury. Okay, or the mercury. Do you think that's healthy? Why not? It's not healthy. Why? What makes you think like it's not healthy? Jill, think about you're consuming some lead. You're chopping something. You're eating some lead. Is that healthy? No one thinks like, hey, consuming lead is healthy. But you used to back into Middle Age in Europe. That though like consuming lead or they putting some mercury on your face is actually healthy for them. So they actually died, and in the ancient China too. Many of the emperors died because of this heavy metal toxic. So what happened there is, because the reason why we call them as heavy is because once they can embed in your body, they don't come out because they're heavy. So and then they accumulate in the body. Gold, it tends to be not treated as the heavy metals, but we're not really eating gold a lot. I mean, this is too expensive. That's one of the reasons why. Gold is known as the non-reactive one too. Yeah, I think Jenny's here. So where do we get the heavy metals from? So generally, we get the heavy metals from many places. On your page 3, there are some examples. We're getting the heavy metals or the hard waters too, or the minerals, or the some of the metals. So salt, anything from the minings. Okay, so and agricultures, domestic sources, waste treatments, plants. So these are the 4 main sources that we get some minerals, something like some harmful minerals into the human bodies, into the environments. So minings, we can get a large volume of the, for example, like coals or some of the heavy metals. Agricultures, we can get a large amount of ammoniums in there because they use lots of the ammonium and sulfate as well for the fertilizer. So you may just think like, hey, would you ever want to live near at the mining place? No, and you don't know that because it's not healthy because there are lots of chemicals can be in there. All right, domestic sources too, phosphate in many detergents induce eutrophication. Highlight that place. Phosphate related to the eutrophications is the main problem of the water environment problems. So, and the last one, switch treatment plants. Yes, there all be some ions in there too. So anything from the industry, anything from the domestic, some agricultures or from the domestic can be harmful. So let's think about why we need to monitor them, because they are harmful. When you consume that, like for example, we are consuming some of the hard water, the heavy or water with the heavy metals, they're not really harmful. They're not really healthy. So some example of the some ions we have on your page 5. So I want you to have a look at the page 5, please. Some common chemicals we can get from the environment, from all the industrial and domestic environments. So we can have the barium, chloride, copper, fluoride, iodide, iron, lead, mercury, nitrate, silver, and sulfate. These are the common, you don't have to write, just have a look at these first, okay? These are the chemicals that you will need to monitor. You will need to learn how to monitor. You will need to learn how to detect it. Okay? Why? So it is very important to know why they're harmful, especially the lead, which is the we can get the lead heavy metal toxicity. Mercury also get the heavy metal toxicity. Nitrate and nitrate can be the algal blooms. All right, silver can be or can cause you the heavy metal toxicity, which means that you can imagine. If you get heavy metals in your body, it can block your nerve cell. So what that happen is, as they block into your nerve cell, even though your brain is ordering to do something, it's not moving properly. Okay, that's caused by the heavy metal toxicity too. Okay, all right, and also we have sulfate can damage the ecosystems. They're also causing some of the eutrophications too, and the phosphate too. So we have think about many reasons why. All right, don't need to know about the ppm values. This is not so important for in chemistry. It's more related to biology parts. So the first part of today's lesson is we're gonna learn about how to monitor them. So started with the some of the questions here, but I was gonna do something. No, I leave the in class at 1.4 now. Let's move on to the page 12, please. Let's start from how to identify cations. Mina, what's cations again? Yep. Cations are the metals. Ions are metals that are positively charged ions. Yep. Okay. The first method to detect the cation is we can use the flame test. Do you remember, like in the different metals have the very specific their flames according to Bohr's model, something we learned in the module 1, but I'm not gonna ask you like how they're working. Okay, flame test. So what we do for the flame test, we use either the platinum wire or spray bottles. Okay, you can spray the some solution with the metals to the Bunsen burner, and you'll see some very beautiful colors coming out from there too. Or you can also use the platinum or nichromate wire, tip it into the the metals, put it into Bunsen burner, and you'll see the flames like this. This is on your page 13. Okay, and we get the very specific colors for the very specific the metals. So for example, sodium would be yellow, strontium is scarlet, copper green, barium is yellow green, lithium is crimson, calcium is red, and potassium is lilac. These are the least colors of the flames you need to memorize. The first part, the first thing I ask you to memorize, this one. You need to memorize this. It will now be the common sense to know the flame color of each of metals. Okay, but let's see, we don't have silver, or we don't have the lead, or we don't have the mercury in that list here, the flame test. Why do you think we don't have those? Because we don't really. Why do you think we don't have the colors for the mercury, lead, or the silver? There is no silver or the mercury or the lead. Why do you think we don't have these in the flame test? Are they? Okay. Let's think about what happened. We performed the flame test, basically. Yeah, I mean, like basically when we put some metals in the flame, means they get easily evaporated. So spraying the lead water, spraying the silver water, or spraying the mercury water, that's not really safe to perform. So we don't really perform that in school, right? Neither in the lab, because they're all heavy metals. So these metals are generally what in the very light group metals, or some of the transit metals only. The reason why we don't use this because we don't want to spray the heavy metals around the room. No, you can inhale it.
That's correct.
Yeah, you're correct. Yeah, you die. Because when you're spraying, that means you're spreading all the mercury, the real particles of mercury in this room too, and we don't want you to inhale that. Same for that too. Same for that too. So we don't really use these for the flame test. We don't recommend to use the heavy metals for the flame test. In fact, we only use this list over here. These are the least harmful, even though you can inhale them a little bit amount too. I mean, like we're not going to burn like a bunch of the kilo of the copper. No, it's for the flame test. We only do the little parts, a little amount. So except these, we can do the flame test, and specifically copper Barium is the one of the most common metals you will find in the school test. And the calcium too. Okay. So this is the first method. We can use the flame test to qualitatively analyze the metal. Okay, I'm trying to going back to this big frame again all the time because we have many techniques, we have many tests coming out. Second part of the qualitatively analyzing metal or cation is we use the precipitation. And this is related to the solubility. John, do you remember what I mean by the solubility? Something is soluble. Yeah, so solubility means the ability to dissolve in basically just generally in the water. Okay. And do you remember that too in relation to QSP and KSP? Mina, do you remember that KSP and QSP values? Yeah. It's given on your page 10. Page 10. Okay. So when we say the soluble is more than 10 grams to be dissolved in 1 liter, this is a quick revision of module 5. Insoluble means that less than 1 gram dissolved in 1 liter. Okay, sparingly or the slightly soluble means 1 gram or 10 gram will in between them will dissolve. We can use the QSP and KSP relationship to remember. You have to remember this as well. When the QSP value is greater than KSP, okay, that means that there will be the precipitate. When QSP is smaller than KSP value, there will be no unsaturated, so there'll be no precipitate. Why? QSP or the KSP is basically about what? Product concentrates the product of the concentrated reactant. Okay, so when we say QSP is bigger than the KSP, simply you can think that as we have a much of the products left is oversaturated, which means that there will be some precipitation reaction. All right, let's try some question related to solubility. A quick revision of the module 5 1.2. Give you a little time to do this question. From the data sheets, the KSP value of the lead hydroxide. No, it was here. KSP value of lead hydroxide is 1.43 times 10 to the power of minus 15. That's KSP of the lead hydroxide. Okay, molar mass of the lead is 207.2. 불 닫기 전에 뭐 사와. 먹을 거 사와. 지금 갔다 오네. 진짜. 닫기 전에 갔다 와. 저처럼 먹지 말고. It's been a while. No, I just ran out actually. So extreme.
No, this is so serious. It's not qualitative. I can't remember how to do this. What?
Measure 5 again. All right. The KSP of the lead hydroxide is given as 1.43 times 10 to the minus 15. So always start from the equation, balance equation. The lead hydroxide PbOH2, which is solid, can be dissolved, and it goes other way around too. Let's make a precipitate. We're going to determine that. It'll be Pb lead 2 plus aqueous plus 2 OH minus. The reason why we need to write that is we need to determine the coefficients are in your product side too, so which will determine the QSP and KSP too. So hydroxide, lead hydroxide, okay. It's now it has, we can, how much we have? Okay. We now have 3.050 gram, or 5 times 10 to the minus 5 gram of lead hydroxide, which is dissolved in 100 milliliter. So let's find the concentration of the lead 2 plus first from the given grams, okay? To find that, we need to find the N over V. The N can also be found from what? The grams. N is equals to M over molar mass. over the volume. So I just put it everything here. We have 3.05 times 10 to the minus 5 divided by the molar mass of the lead, which is the same as the, for the lead hydroxide, sorry, we need to think about like the same as the concentration of lead hydroxide as well. I forgot to mention that means that the molar mass part, we need to add all the molar masses of the 207.2 of the lead and 2 times 16 of the oxygen and 2 times 1.08 for the hydrogen. Yep, that means you can find the number of moles in the given that grams divided by volume, which is the 100 mil, that's 0.1 liter. Okay, and then you should have the lead concentration must be 1.26 times 10 to the minus 5 mole per liter. Everyone good up to here? Okay, pretty easy process up to here. What about the hydroxide? As according to the reaction, the coefficient we have 1 to 2 means that the concentration of the hydroxide or the number of mole of the hydroxide must be double of that. So it would be 2 times 1.26 times 10 to the minus 5, which is 2.528 times 10 to the minus 5 mole per liter. From here, we can find the QSP, not the KSP value, by that QSP is equals to lead concentration times hydroxide concentration and square that. Okay, everyone got up to here? And substituting this value and this value into here, you should have the QSP value, which is 8.08 times 10 to the minus 18, which is smaller than, 15 should be 10 to the minus 15.
Why is it 15?
I don't know. Check your answer. 10 to the minus 15, which is greater than your KSP value that was 1.43 times 10 to the minus 15. So, John, we have a QSP bigger than KSP. Will there be a precipitate or not? Yes, so as this QSP is bigger than that, there will be the precipitate. Will form. Okay. You do not need to construct the ice table, by the way. As we just simply need to find from the given, if that's all dissolved, then will there be precipitate or not? This is what we need to do, comparing the QSP and KSP value. Yep, quick revision on the module 5. But why am I talking about this? Because this is related to some solubility, which is the precipitations in module 8 as well. Means that there is a chance of mixing up the module 5 and module 8 together. So giving you the questions like this, and I can ask you what kind of the metals or what kind of cations, anions in there. All right, so let's talk about some solubility related precipitations. Lucy, do you remember the some rules for the precipitations? SNAP rules, yes. What's the SNAP stands for? Sodium, nitrate, ammonium, acetate, and potassium. And these are always soluble, means it never forms, the precipitate. They do not form the precipitate. So this is the reason why we commonly use the making the solution as ammonium something or the something nitrate a lot. Okay, it's good to remember this. I mean, just essential from year 10 or 11 that they are not making any precipitates. Besides them, you need to know some precipitates, common precipitate of cations of silver, lead, barium, calcium, magnesium, copper 2, and iron 2 and iron 3. How many? 1, 2, 3, 4, 5, 6, 7, and 8. At least 8 metals. For example, Mina, what is the precipitation color of the silver hydroxide? Brown, as we have a brown in here. What about silver chloride? White. That's all you need to remember. No, everything. Everything. I hope so. So for the silver, it's a very common type as well. But there's just one simple rule. There's only one rule we can find in here. On your page, what page is this? Page 14. Okay. Second dot point, third dot point. Main groups metals forms a white precipitate. Highlight that. Main groups as in like calcium, magnesium, but we don't really count the potassium, sodium. Why? They are group 1 metals. They do not form the precipitate because they are reactive 1. So we probably start off in the group 2, which is like a calcium or magnesium, which is part of here. And as you can see, the calcium, magnesium always be what? White. Okay. So mainly there'll be a white. So start off from that. And then barium only forms a precipitate with this sulfate. This is also important to remember. Barium doesn't form any precipitate with the chloride or the phosphate or the hydroxide. Okay. Lead, something that we learned is something very toxic. So let's going back to the cations from the flame test. Lucy, we said like silver and mercury and lead is not really detectable from the flame test. Well, let's go without the mercury. Mercury is quite easy because it's only liquid metals in room temperature. We can detect that quite easily too. So let's go for the silver and the lead. If we cannot detect the silver and the lead from the flame test, is the plan B would be, or plan A would be this precipitations. So what we do if we know there's either silver or the lead, we add a hydroxide, yes. And then what do you expect? If we have a silver, good. Can we put the chloride, for example, hydrochloric acid? They're both will be white. So in case we have a both white colors to precipitate, we cannot use that for the detection of the silver or the lead. So the color is important because it will give you very what kind of cations you will have by putting what kind of the chemicals you're putting in too. You all right, Mina? Okay. One more thing about ions. Ions will be revisited again too. Iron 2 and iron 3, it has the same element, but you see that iron hydroxide XB with the green, whereas iron 3 hydroxide would be the brown. Another thing about iron 2 and 3 is it's about the permanganate and the thiocyanate. Okay, only the iron 3 will be the deep red with the iron and thiocyanate, which we learned in where? Module 5 again. When we learned about the equilibrium, we learned that hey, iron thiocyanate is a red color. When you give it heat, you increase the concentration, they change the color to brown or to the colors. Okay, so remember that too. Iron 2 will only be oxidized with the permanganate. Now with the iron 3 plus. Okay, there's a very clear type of the precipitation reaction we can use. Iodide is the only be detectable with the silver or the lead as well, with the yellow precipitate. All right, any questions about the precipitation colors? Not really? Yeah. Precipitate here.
White greater than 0.05.
Okay,
So
yep.
does that
Means that in the higher concentration than the 0.05 molar. So for example, if you use the hydrochloric acid that has a greater concentration than 0.05 molar, there will be a white precipitate. Means that they are spanily soluble. So it requires a kind of higher concentration, some special condition too. Same for the calcium hydroxide, it requires a quite a, like some certain like high concentration value.
Can we test for silver and lead together with HCl but have lower concentrations of HCl?
That's kind of vague though. I mean, it's inaccurate though. It could be inaccurate. As first of all, there could be some precipitate formed with that, even for the low concentration of the hydrochloric acid. There's a chance, and it can confuse you that whether that's the silver or the lead. So probably the safest way, probably the definite way is you use something else like hydroxide or the sulfate. So you would clearly see the difference in there. Okay, so I know there's some concentration written here, but don't just think too much about the concentration given. It's more about the colors of precipitations. Okay, concentration would not be like in a big matter. All right, second method is, so some of the precipitation we have in here, especially this hydroxide column here, especially the hydroxide here, some of them are actually not known as the complexations. So the third method we use to detect the cation is known as a complexation. Okay, what do we mean by the complexation? Complexation means we're making some complex ions. So on your next page, page 15. The process called the so let's think about the transition metals. I'm not going to bring up some of the SPDF rule in here, but transition metals are basically located in the D block in your periodic table. Okay, as we learned in the module 1, it's SPDF. D block has about tens of the electrons, means that there are high density of electrons compared to the group metals. So unlike the this is the reason why the transition metal can have the various valencies. For example, ions and coppers and lead, they can have various valencies because there are too much, a huge density of the density of the electrons, which will vary the amount of the valence electrons too. Now, another thing about the D block is they can form something called the complex ions. Okay, why is it called a complex ion? Because the high density, the electrons can attract this some other form. So for example, we have complex ions look like this. We have one cobalt with a 6 ammonias attached. But when you're writing the N, so make sure you show the N, the nitrogen is attached to this. Let's see, make sure the nitrogen is attached to that, not the other part too. It's also written on your page, even on your page 16, and you see the lone pair of the nitrogen will be involving in that reaction like this. So name of that would be cobalt hexanitrate complex ion, and you will carry the 2+ of the net charge. This is known as the complex ion, and this only happens in the transition metals, such as we learned about the copper, okay, iron 2, iron 3, and some of the lead probably. And when the ions, the metals form the complex ions, they change the color. There are specific rules for the complex ion too. So as you can see from the complex ion here, we have something called the central metals or metal ion inside. So the metal ion inside there. The branches here, each of branches called the ligands. So in this case, we have 6 ammonia ligands attached to the central cobalt metal ion. The way we express the complex ion is we write it as this. When we have metal ion, when M+ metal, the aqueous will be combining with the number of the ligands, and L aqueous, and this will be equilibrium to becomes the complex ion of M, L, and the plus like that. So the full equation for that, this cobalt is, we have a cobalt, so this is what? CO2 plus, for example, plus N, which is 6 ammonia, NH3, aqueous to becomes 2, CO cobalt, and the NH3 6, and carrying that 2+ charge in here. This is 2+ is coming from the cobalt because there's no charge in the ammonia. Make sense up to here? So the types of ligands we can have, we can have NH3 ammonia can be attached, okay? Or we can have the OH minus, we can have the H2O, or sometimes the carbonate, CO3 2 minus. But these three are probably the most important parts in this question for this module A parts. Which means that instead of the NH3, there'll be OH minus can be attached. Instead of the NH3, the H2 can be attached too. But when we have the different ligands attached to the same metals, this is important. When we have the different ligands attached to the same metals, they can change the color of the solution. So for example, on your page 19, we have some example of the chromiums. We have 1, 2, and 3 solution here, 1, 2, and 3. So we have 3 solutions with the chromium, complex solutions with the chromiums. One is the hexahydroxide chromium. So we have 6 hydroxide attached to that. Second is we have ammonia is attached there. Third part, we have ammonia and some of the chlorides is attached to that. Okay. But Lucy, do you see the color difference between 1, 2, and 3? What's the color for the first, the flask? Blue or purple? Blue, moist blue, blue, purple, bluish purple, blue, purple. Second one is yellow, and that is green. Why do you think there's a change? There's a color differences between these 3 solutions with the same metals? Exactly. So we have when the different ligands attach to the same metal ions, they can change the color. And some of these colors that you need to memorize too. I will pick the very specific colors and very specific ligands that you need to memorize at the end, but good to know that how the ligands are formed. They can.
They get.
Never thought about that. Sorry. You can still do it. So I mean, there's color is not the only one. They can determine the what type of chemicals they have. There are various ways. Maybe they're using the precipitations. Maybe they can use the something called the AAS later on, or colorimetry, or some other tools. So rather we use a precipitation a lot in the uni lab or the pharmaceutical labs. They're actually using the more higher technologies, but they can still do it. But there could be some limits. Okay. All right. So different ligands. So answering this question, explain the difference in the color between the 3 complexes as the different types of the ligands attached to the same central metals. Okay. They will appear to have the different colors. So you can just explain that as the ligands present in ligands is the factor that giving the different colors in that case. We can think about the oxidation states or the essential metal states too, but let's not go to the oxidation state here. They will have the same oxidation state by the way. Okay, they will all share in the same type of the metals in the central. So means that the only factor that they can give the different colors is the type of ligands they are attached. Okay, let's practice a little more about the forming the complex ion phase. We can use this empty space on that page, same page. There, what question was that? Okay. To question 19, page 19, use the space. Assume that we have one silver plus the 2 NH3. Okay, can you guys write me the complex ion form from here? And if you can draw the structure of this, that'll be nice. The second one is okay, let's start from this one first. When these are formed, the complex ions, what could that be? Next one you can do, copper 2 plus there are 4 Cl minus. This also could be one of the ligands too. Or it could be the complex ion. Write it down, the complex ion formula. And I'll show you the structure too.
Is it always 6 ligands?
No, it depends. Yeah, that's something you will be given. You don't need to memorize how many ligands will be attached there. That's too much. Because it will be related to the SPDF, like hybridized, something about that. Sorry about it. Na3, NH3 is no, ammonia is 0. Ammonia doesn't have any valency. This is ammonium. No, it's not trick. So, okay, the first one, when the silver has the 2 ligands of the ammonia, it will be like this. There will be silver. Okay, this is how you write it. You need to write the the metal first, silver, bracket, and ammonia, which is your ligand, and write the number for the ligands. Okay, Jiang, is there any charge on the ammonia? So even though I'm adding this, the charge is 0, I'm adding to the plus. So what if the net charge? Plus. Okay, but the structure formula, you can copy this down too. You can show that the silver is in the middle, like this. It will forming a bond with the lone pair of the NH3 and the lone pair of the NH3, like this. Make sure you show that the lone pair from the nitrogen. Don't put the NH3 like this. I mean, this is different. Yes, we are very picky. So make sure you NH3 like that and show that in the big bracket with the plus. This is how you show the structural formula of silver dinitrate silver complex ion. Yes?
If you're given that there's 2 ligands, one on one central atom, would you assume that
it's a linear. Y is always be, yes. What about the next one here then? Copper 2 plus 4 Cl minus. I mean, the structure of that would be most likely to be the tetrahedral then, or the trigonal planar, depends, but the structure is not like a big like matter. I don't think like get questions about complex ions as you didn't really learn about the complex ion in details. Asking here. All right, when the copper 2 plus is having the ligands with the 4 Cl minus, the way we write it that is start from the copper, Cu in the metals, and then Cl to worry about the minus, okay, and then write down the number of the ligands 4. But as per Cl carries a 1 minus, and we have 4 of that, the total charge will be 4 minus here. We only have 2 plus here, which means 4 minus 2 plus would be 2 minus in net charge. So in case of the ammonia, we don't carry the acid, they don't carry any charge. It will follow the charge of the metals, not for the chloride or the hydroxide too. Everyone good up to here? Okay. All right. Could you guys do the same thing for iron? Iron 2 plus 6 H2O. And draw the structure too, please. Think about which part of the H2O has the lone pair. Yes. So this is known as a hydrated iron too, complex iron. And it will have certain colors too. We're going to talk about the colors in a second. But the way you can show the structure is putting the iron in the middle, okay? And make it 6. 6 should be like this, or the bondings. Now, water has the lone pair on the oxygen side, means that put our oxygens first and put a lone pair of the oxygens, just one pair of the oxygen here, like that, and attach the H2. Like this. Or H2O, you can H2O, H2O, it doesn't really, this is not pretty. That's better. Okay, this is how you can show you that with the bracket 2 plus for the complex iron. Okay, why do we need to learn about this? Okay, yes, you may get questions about, hey, we have this and this, which is the ligand, which is the essential iron, essential metals, and what would be the formula? Draw me the structural formulas. It's good to know some of the this complexation ion structures and how to draw them. Did you get that? Okay. And also, it is very important to know the colors of the complexation ion. So it's on your page 20. And the table of it down on here. Commonly, the tables given on your page 20 is very important. So we have given lead, silver, copper 2, and iron 2 and 3. And you can highlight that the lead would be colorless complex with the excess hydroxide. So when you're working with the hydroxide, server produces colorless complex, the ammonia, colorless complex, and produce a dull, almost colorless, luminescent complex with the cyanide. Copper is blue complex with the ammonia and the water. And iron 2 is green complex with the water. Very importantly, most importantly, iron 3 is yellow complex with the water, and the blood red complex with the thiocyanide. But something that we learned as a precipitate is in fact known as a complex ion complexations. So I can give you this example here. Assume that we have lead and the silver, lead 2 plus and silver plus. Okay, John, what happened to this when I add HCl? When I add HCl, adding HCl means I'm adding this chloride to this. So would they form any precipitate? You can look at your tables, not on there. Page 14, 15. Yep, that one. If I add HCl in here, would they form any precipitate? Yes, what type, what color? For the lead, white, silver. Chloride is, that's both the white. So we just discussed that, hey, putting that hydrochloric acid to that is not really possible to this. But if we have no option, just hydrochloric acid, and we both get a white precipitate, what we can do in the next step is we can add some nitrate, add diluted NH3, ammonia. Why? Lucy, what happened to the silver chloride when I add some ammonia to it? They decolorize it, means that white precipitate will be, the AgCl will be decolorized or will be dissolved. What about the lead chloride? Is there any reaction to lead chloride with the ammonia? Not really. No reaction. Which means that adding the dilute NH3 would make this to be what? Just be the white precipitate too. Okay, so this is known as a secondary second conformation process. If we don't know which is this from the, as they have the same color of the precipitate, we can always go for the second process. Sometimes they use complexation, sometimes use the precipitations. In this case, with complexation. This is well described on your page 22 on the flow chart in here. When we get the silver and the lead. Yep, on the silver and the lead. And when you put from the silver lead, when you're adding the from the white precipitate, adding the dilutes, the ammonia will make dissolve the brown precipitate dissolve in that, or they make it forming the white precipitate. Okay, well, let's have a little break, and after that, we're going to discuss more about the flow charts too. Memorize all the flow charts.
He memorized it and he wrote it in the exam and he and then used it in the exam.
아, 선지 와서 써야 되는데. And I can bring him here. I can ask him to just write down all the flow chart in here. Lucky you, Sanjay. All right. So let's think about some cases we have. Assume that we have unknown cation. So this is like this. Mina, assume that we have a flask. In that flask, we have some solution, unknown solution. Okay, what we know is it has either nitrate, silver, barium, calcium, lead, or the copper, aluminium, iron to iron 3. We don't know what's in there. So what we have to do is we need to construct a method. We need to do the test. The first step we can do is, so I'm gonna, using the flowchart, I'm gonna write down the methods here. So you can copy this down on your space provided. So what you have to do is take a sample first. Okay, After you take a sample, what you do is you put some add, so take a sample of say 10 milliliter. If you're taking like a sample of 10 milliliter, so it's about this much in the test tube, add about 2 milliliter of the dilute. Say, let's go for dilute, the HCl. The concentration would be like 0.01 molar or something less than that. It doesn't have to be a big concentrated hydrochloric acid, because what we aim to test here is we are testing for whether there will be a precipitate or not. Okay, so using that, see that if there is a white precipitate, it's either to be, so using the flow chart here, it's either the cation should be silver Ag plus or the lead. As we learned that white precipitate is only formed with the silver and the lead. Make sense? Okay. So I'm going to separate them from here, because in case we have a white precipitate, in case we don't have a precipitate. So I'm going to continue from here too. If there is no precipitate, okay, what you do? It must be the others. So what we do, we put add some more dilute NH3 to the second sample. Same in here. So in this white precipitate part, we also do the same process. We add dilute NH3 to a second sample. And Lucy, what happened to the silver when this reacted with the nitrate, to ammonia, sorry? What was the reaction between ammonia and the silver? It turns brown. So depends on the concentration of ammonia, it may turn to silver, will turn to brown, and then colorless. So if you can observe that there is a brown precipitate and then turn colorless, it can confirm that that must be silver from the white precipitate parts. Okay. What about lead, Mina? Lead with the dilute ammonia would form the white precipitate. Okay, I'm using the flow chart to writing down the proper methods. Okay, this is the first part. Second part, okay, if we didn't get the white precipitate, we add the same procedure, collect another second sample, add the ammonia into there, and you see the various colors here. So think about some of the case of the precipitate. If we have white precipitate, that means it must be the aluminum. Make sense? Okay. If we have the pale green precipitate, that'll be the iron 2+, because iron 2+ have the complexation with ammonia to become the pale green. Third is iron. We have a brown precipitate or brown color. It forms brown. The solution turns to brown. It must be the iron 3+. Okay, also the blue precipitate would be copper. That's the case in case of the there is a precipitate. In case we don't have any precipitate with the second sample with the dilute ammonia, then what we do the flame test. On the third sample, in case there is no precipitate in the second sample. So what we have expected from here is if the flame test, it shows a red flame. Red means it will be red flame would be the calcium 2+, and the yellow green would be the barium, and no color would be the ammonium, sorry, NH4+. Okay, this is just one sample of the flow chart. We can do the various things. So what would be the other methods? I mean, this is so we started from the dilute hydrochloric acid and add the dilute ammonia to detect the precipitate reactions. In case there is no precipitate in the second sample.
Also, is this distinguishing one unknown cation?
It will definitely distinguish one anion. So assume that in the sample given here, we don't know what type of the metals in here. So we can do the various methods, but this is one type of method to add some hydrochloric acid. So let's think about here. You know, I have taken a sample and I put the hydrochloric acid, and there is no precipitate. In my second reaction, I put some dilute the ammonia, and there was no precipitate. Yep. Then I decided to perform the flame test. I observed that they were showing the pale yellow-green color. What would be that cation? It would be a barium. So it's like the flow chart thing. Like you need to go order by order. But it doesn't have to follow this order all the time. I mean, you can start with the ammonia instead of this. So assume that we have started with the ammonia instead of the dilute hydrochloric acid. So let's make a new flow chart with the ammonia using the tables we had. And we are having the same things. So from unknown cation, do you have a space in the next page? Yep. So you can use the space below here. This is for the NaOH. I'm making another thing. So you can make a third flow chart with the add the NH3 ammonia first. So let's think about this. You have unknown cation. So I add some dilute NH3. Okay, so using that flow charts over here to think about what happened to the NH3. Adding the NH3, there will be some parts there will be precipitate, there will be no precipitate. Okay, so this part will be no precipitate. Shall we go for the no precipitate part first? Think about the information that we had. No precipitate part of the base is either to be calcium, barium, or the ammonium. So it'll be either, but how are we gonna differentiate the ammonium, calcium, or the barium? So without using the flame test. Okay, let's bring up the precipitation table on your page 14. Ammonium is the one that doesn't form the precipitate. So we have to determine the calcium and the barium. Lucy, how are we going to differentiate the barium and calcium? They both react to sulfate. So we can't put the sulfate. To distinguish the barium and the calcium, you may choose the hydroxide or the fluoride. because calcium is the only one that forming the white precipitate. So what you can do in the second stage here, add some sodium hydroxide. As a result of that, you will see the calcium 2+ will be the white precipitate. Okay. And barium 2+ would be a no precipitate, no reaction, and ammonium 2, no precipitate. Then how are we going to differentiate these two? They can use the sulfate or something else. Okay, you can add the sulfuric acid, H2SO4, to differentiate barium. So barium will now forming what? After that, adding this, barium would form the white precipitate. Ammonia will be no reaction. I'm adding that, add NaOH and add sulfuric acid, and there's no precipitate. Okay, now what about the second part here? So adding the dilute NH3, so there will be some precipitate. Let's talk about the precipitate with the ammonia then. You can use the flow chart here and given here, okay? All right, so from the flow chart given here, adding the NH3 on this column here, we can have a precipitate of the brown, white, white, pale green, brown, and blue. Yeah, so we have a colored precipitate, we have a white precipitate. So we can divide the flow chart into two parts, white and the colored precipitate. In case of if we have a white, it's either to be what? It's either to be lead or the aluminium. It's either to be lead or the aluminium. Colored one, we can distinguish that quite easily, but we can also have some brown. We also have the pale green. There is the blue. Mina, when we have the blue precipitate from the dilute NH3 ammonia, what is this? Blue must be copper. What about pale green? Iron 2+, good. Brown or brown upe. It's more likely to be iron 3+, more likely to be, because we can also have the silver too, but the silver can be dissolved on the excess, but we will be dissolved. So you can see the dissolve in excess NH3. Or if you want to test for the brown precipitate here again, what you can do, you can add HCl for the third conformation, and you will expect to see that the white precipitate on the silver and no reaction. And this would be white precipitate would be silver, as that forms the silver chloride, and there'll be no there'll be iron 3+. Okay, from the white precipitate part, the lead and aluminium, okay, how do we determine them? Aluminium actually can be dissolved too, but the way we can determine the lead is pretty easy. So what you can do, you can also add HCl in here. John, what happened to the lead when we add the HCl? Adding Cl to the lead, there will be white precipitate. So we get a white precipitate from this one here. That means that there must be the lead 2 plus. No reaction, that'll be aluminium. I think last year in the Knox grammar, they had this question asking you to construct the flow chart. We're using started from the dilute ammonia like this. So, there's a chance you get a depth study about this. Yes, there's a chance you need to ask to construct a table like flow chart like that too. It's not going to be that kind of complicated. I'm using all the type of the cations we can think of. They will only give you up to 4 to 5. But this is a very common type of the chemical reaction, chemical flow chart we can think of too. All right, another method we can use is that we add sodium hydroxide instead of the ammonia. As we can say, adding the sodium hydroxide to the sample, we can get color precipitate, no precipitate, white precipitate, something we just did in here, like this. Okay, in case we have white precipitate, hydroxide would inform precipitate with the lead. Okay, and then calcium and magnesium. Okay, calcium, magnesium also forms the white precipitate with the hydroxide. Therefore, we can determine that with the sulfuric acid here too. Yep.
This part isn't meant to be ammonium that we're trying to.
That means ammonium, yes. So it means that will be barium. That will be the ammonium. That's NH4 plus should be. Okay. So for the white precipitate part of the sodium hydroxide, we can get that. Color precipitate, we can green, orange, brown, and blue. So green precipitate must be the iron 2, blue precipitate must be the copper, orange, brown would be the either to be iron 3 or the silver 2. Something that we covered here as well. We can determine from the adding the sodium chloride to form the sodium chloride 2. Do you see like some duplicate? Like no, I'm using there is common anions here. I'm either using hydroxide, chloride, or the ammonia. Well, here we don't have the ammonia. We sometimes use a sulfate. So it is very important to use sufficient and correct anions to determine which is it. In case we do have no precipitate, there must be barium and calcium. So we put some sodium fluoride. We can use that precipitation tables to determine which is which. Okay, but I think that Sanjay did that. Don't memorize this flow chart. If you decided to memorize flow chart, memorize all these 3 different type of flow charts. It will help. But start from the precipitation table. That's the first part you need to do. So try the question 1.3, question 1, 2, and 3 now, please. We can go through question 4 together. All right, in class exercise 1.3, so question 1, hydrochloric acid added to the solution causes no change, but the addition of NH3 leads to a brown precipitate. Identify the metal ion present. So we have HCl, Cl is added, but no precipitate means that it's neither to be silver or the lead. So the only case we have the brown precipitate with the ammonia will be iron 3 plus. That's the only case. Okay. Question 2, hydrochloric HCl added to a solution causes no change. Again, no, that means that you can just justify. You can have some practice on, hey, what does that mean? There's no precipitate on HCl means that it's neither to be silver or the lead. Okay. And then nor does the addition of the NH3. Good. A flame test performed and then the red flame. As we have a red flame, from the flame test, it must be the calcium 2 plus. This is a metal ion. When you're writing the metal ion, make sure you write the valency stem too, because the ion 3, ion 2 have a different distinctive the valency. Question 3. Often when testing for cations, if the presence of a certain cation is found, a confirmation test is then carried out to confirm its presence. A, outline the need to confirm the presence of cation. Why do we need to do why do we need to confirm the presence of the cation? Like, for example,
the silver chloride and the silver
lead chloride, you mean?
lead,
Yep.
Since the color is the same,
Mm-hmm.
test allows us to identify which have iron shares different results.
Very good. In case some cations have the same precipitation color. For example, the lead chloride and silver chloride. A confirmation test is required to clearly distinguish those cations. Very good. B, a sample forms a white precipitate when tested for with a small amount of sodium hydroxide. Okay, sodium hydroxide. Suggest what ions is present and what steps should be undertaken to confirm this cation present. Jiang, we have sodium hydroxide. So adding sodium hydroxide means we're adding the OH minus, and we got the white precipitate. Okay, so what could that be? What cation could that be? It's sorry? It's either to be calcium, yep, or magnesium, or lead. Lead form the white precipitate. Yeah, okay. Lead 2 plus, anything else? Okay. 그러면 how are we going to identify which is which? What would be a second test? You add H2SO4 on this new and on a second sample. And what do you expect? What precipitate color? White precipitate, white for the calcium, and no reaction. What about the lead? Does lead form any precipitate with the sulfate? I don't think so. Why?
Because it shows that if the precipitate dissolves, it's PB.
Maybe, but is there any other method to identify this? I mean, we can do that, and maybe that, I mean, both of the magnesium lead would not show the precipitates. Means that you may need to think about putting some hydrochloric acid. As we know, lead will form the white precipitate with the chloride too. There'll be a third. So you can add HCl, then white precipitate would be the lead. This is one method. It's one of the many methods. Okay, but do not perform a flame test. We have lead. We may have a lead, so don't perform the flame test. We can't do that. Okay. Any other method from you, Lucy? This is one method: adding some sulfuric acid and hydrochloric acid, and we can identify which is which. Any other methods? Okay, not really. Sulfate, calcium, magnesium, lead. Maybe we can start from the hydrochloric acid first. Okay, putting the hydrochloric acid, then what do you expect for the calcium and magnesium? No precipitate. So if there's a white precipitate, there must be a lead too. And then putting the sulfuric acid, yes, you may get that. Okay, so there are various methods you can use. You can also use some of the different type of the anions to see whether like they have a precipitate. All right, good. Question 4. Let's go for question 4 now. Excess value of sulfate will dissolve a silver chloride precipitate. The complex that is produced in the linear complex. Explain the use of the chemical equation, how this possible can be identified cation present. Okay, don't worry about this question. The complex ion, this is like out of the syllabus now. All right, what we have, I mean, I should have put that question in before. Open at page 30, please. Could you guys try to do question 1 and 1A, B in class exercise 1.4, question page 40. What should we put to see the some precipitation of the copper? You should know.
Is it come back?
Yeah. it's not a closed book test.
And then
So you put adding some sodium hydroxide, and what do you expect? It's turned into blue. It means that blue precipitate of the copper hydroxide. Anything else? What about the ammonia? Would copper form the complexation with the ammonia? Copper?
Oh no, copper doesn't.
Copper does, yeah. So you can add some dilute ammonia to also get the blue precipitate. Oh, it's kind of rule for the copper. Copper is always with the blue then. Anything else, Lucy? Yep. See whether you can dissolve in from the excess ammonia too. But just let's talk about the blue precipitate, because blue is probably the only color for the copper.
If it's
Mm.
it's already a blue solution.
Mhm.
Can you
You get the precipitate, like some precipitate, which means undissolved the salt. Good. Next one, calcium then. No flame test. Jim, how are you going to detect the calcium just using the precipitation test? What chemical what anion should we put it in? You put the hydroxide, so either put sodium hydroxide, and what do you expect? Calcium? Calcium? Ca? I'm doing question B. White precipitate? Yep, so if you see the white precipitate of the calcium hydroxide, yep, that must be the calcium. Anything else for the calcium? Fluoride too, so we can also put the HF, hydrogen and fluoride. And what precipitate color? White as well. And remember that the calcium is your main group, so the precipitation color will always be white. Yes? For the OH, with the calcium, is it where written in the flow chart?
NAF to get this.
That's interesting. Maybe some false information then. Calcium. Oh, that depends on the concentration. So in that case, they're assuming that the concentration is lower. So that's only case the concentration is greater than 0.05 mole. So I think that flow chart is indicating that the lower than the amount of the concentration of the sodium hydroxide is lower than 0.05. In that case, yeah. Yeah, bit general. All right, this is how we use the precipitation reaction to determine the cations Let's move on to the anions. Okay, open up the page 427, please. All right, there are a few ways as we can identify the cations. There are a few ways that we can identify the cations. Okay, the different parts of the anions, the cation is there is no complexation. Because the complexation is a very unique property of the transition metals. There will be no complexation. There will be some precipitation, by the way. So for the first part, we can test for the pH test or simply use the litmus paper. So Lucy, do you remember the red, when the red turns to blue in the litmus paper? It must be RBB. Alkali, RBB, bar is blue turns to red, means it's acid too. So from the anions, we're having the carbonate, acetate, and hydroxide. They're all basic alkali anions. So if we in the sample we're given, if we have hydroxide, carbonate, acetate, and we can test for the litmus paper, as they are alkali, we can use blue litmus paper. If that turns to red, it must be the alkali. Sorry, red to the blue. Okay, other like the precipitation, we can use the chloride, bromide, iodide, hydroxide in there. But it's kind of general that we started from the silver for the anion, for cation. Why do you think we use silver for the precipitation test for the anion? There we go. Silver causes many of the precipitate. So for example, silver can cause the precipitate with most of the halogens. Yep, and it means that we can separate them from there. So we can use the information to construct a flow chart like this. On your page 29, flow chart 2 first. So without using the litmus paper, first of all, we assume that we have unknown anions. We put some silver nitrate. Again, reason why we have silver nitrate is because nitrate doesn't form any precipitate. It comes in the solution form. So we put some drops of the silver nitrate, then you to see whether there's forming some precipitate or not. So with something that's not forming precipitate, would be with the silver, will always be nitrate, or the sulfate. Okay, nitrate is the one that never forms a precipitate, so we don't need to worry about it. But sulfate can form the precipitate. We just did that. Sulfate can form the precipitate with barium only. This is important. Barium can form the white precipitate with the sulfate. We go to vice versa. It means that sulfate also can form the white precipitate with the barium. So if you get the white precipitate with the barium, that means it must be the sulfate. Okay. Jen, what was the color of the silver chloride again? White. What was silver iodide? Silver iodide? Yellow. Silver sulfide is? It's not given there. It's a black. So white precipitate for the silver chloride, but it also have white precipitate with the silver carbonate. Silver carbonate too. It's not really given on your question, the cation part. Carbonate can be the white precipitate. So how do we test for that? In here, we use the process of the pH. So we're adding some HNO3. Lucy, what's the property of the HNO3? What's the property of this? No, this is called the nitric acid. It's acidic. Is it a strong acid? Yes. Means that we're adding that. So if the precipitation of the white precipitate, we get the precipitate, if that dissolve with the acid, it means that they must contain some kind of alkali. So in the white precipitate dissolved by putting some high nitric acid, which is strong acid, there must be the carbonate, which is a base property, alkali property. Same for the phosphate, it carries some of the base property itself, just itself. Makes sense, okay? So we are choosing the nitric acid. Okay, Mina, why do you think we can't use sulfuric acid or the hydrochloric acid, which are the very strong acid that commonly used as in the lab? for the second test. Why do we need to use a nitric acid? Why can't we use them? Why can't you use sulfuric acid or the hydrochloric acid? It's not there. It's not there. I want you to think. I want you to think about the HCl, H2, SO4 compared to HNO3.
This nitrate and it doesn't because they're basically
There's no precipitate. Very good. What about the Cl? You can make them quite a lot of precipitate with some of the various cations. Means that the hydrochloric acid here would actually can react with some more of the silver presented here too. Means that we're adding some chloride on the top of silver. So there's no point. There's no point. We cannot detect it from there. The reason why we use the nitric acid is it is the least reactive with the cations compared to other types of the strong acids. Okay, this is why we choose to use that nitric acid, not the hydrochloric acid, nor the sulfuric acid. Sulfuric acid we have here, sulfate can form the precipitate with the barium, so we don't do that. And same reason why we don't use the barium chloride. We use barium chloride too. Barium. Can you also use barium nitrate? We can if you decided to, but we want to differentiate the nitrate in there, so we use barium chloride. Okay. There's a reason there, very specific reason why we choose a very specific chemicals to distinguish that. We can't use the same chemicals to distinguish the chemicals. For example, here, in the test 2, we can't use barium nitrate. Why?
you have to find what the nitrate has precipitate.
Yeah, because we need to find whether we have nitrate in that sample or not. And what's the point of putting more nitrate in there if we have a nitrate in it? This is the reason why we choose something different. Barium chloride, maybe the barium something like barium acetate, maybe. Okay, same reason we and then we get this kind of why this precipitate. This is one method again for detecting the cation anion. Second method, or the first method we have, is we use the pH test, the previous page. Again, hydroxide, carbonate, and the acetate. They are known to be the most basic parts too, okay? They're alkali. So basically when you put the red litmus paper, when it turns to blue, it must be either this. Okay, but John, do you remember the reaction between carbonate to the some acid? Carbonate plus acid. When carbonate react with the acid, so it's say HNO3 again, choice of the HNO3 is because the NO3 is the least reactive acid with the cations. What do we get? When the carbonate react with the acids, we get some reaction between acid and carbonate. We get some salt, water, and CO2 for the carbonate and water. Sodium carbonate, potassium carbonate doesn't really matter. Okay, which means that by putting some the nitric acid, if you see them bubbles, if it's some bubbles or the CO2 gas present, okay, the way we can determine that's a lime water experiment too, we can see the bubbles either. So it's in bubbles, that must be the carbonated. So we can distinguish the carbonate from the bubbles. If there's no bubbles, it must be the hydroxide, or the acetate. In that case, we add some copper. We put some copper. As the copper will form the precipitate with the OH, and there will be no precipitate with the acetate. Again, acetate is the one I'm making no precipitate at all. So find something that's forming the precipitate with the hydroxide. All right, so in case we have none of that, again, we put some silver nitrate with the nitric acid. So follow the same procedure as before. Okay, this is the second method, but still, the way we can do thing here is we start with the silver nitrate and followed by the nitric acid for the anion detection. Okay, let's summarize this. Cation detections, cation analysis of cation. We can start from either dilute hydrochloric acid, NaOH, or no. We can either start from adding some hydrochloric acid, NaOH, sodium hydroxide, or the dilute ammonia. It's either three. Okay, maybe you can change that if you like to. That's fine. For the analysis of the anions, we started from different litmus, red litmus, or the silver nitrate. But whether you use the first or second method, you're going to use the silver nitrate, silver, in most of the cases, because silver is the one that forming the precipitate with the halogens, and it forms the precipitate with a lot with other type of the anions. Yeah, then we add HNO3 to distinguish those precipitates, because silver can form the white precipitate with the chloride as well as the carbonate sometimes. So we use HNO3 to determine that whether there will be neutralization or not. Okay, so I try to simplify this flow chart, simplify these tables. There's a lot of things you need to memorize even in the chapter 1. Yeah, there are more coming. Okay. Let's have a look at some questions related to this. So on your page, okay, 31, question 2. I want you to think about this question for a while. It's worth it to think about this one. Okay, for the question 2, it's not in. Mina, we have HPO for 2-. Assume that we have that. Okay, this is aqueous. What is the property of the HPO for 2-? Will there be would this be working as an acid or base? Or both? Both. It's ambiprotic. Good. Means that it can go through the reaction, equilibrium, the reverse reaction with. It can working as an acid to becomes release the 1 proton and PO4 to 3- aqueous. This is known as what? Phosphate. Okay. It's not a blood thing yet. Well, it's something similar. Phosphate, carbonate. Yep. Now, question saying, hey, we have some acidic conditions. Listen, what does it mean by the acidic conditions or acidic environment? Or what does that mean in terms of the hydrogen ion? Well, when we have it as a pH less than 7, means do we have a lot of the H+ available? Yeah, means that excess H+ in there. So assuming that we are putting some sort of phosphate and try to make a precipitate in the acidic, so in acid, for example, strong acid, maybe. So what happened here is, in order to form the precipitate here, we need to have this. So to form, in order to form precipitate, the PO4, the phosphate ion, must be present. But what happened here is, in an acidic solution, where we have the excess H plus. Let's think about in terms of the Le Chatelier's principle here. Come on, this is a big revision here. We have excess H plus, means that we have excess H plus in your product. So we have many of this. Then what happened to the equilibrium? It will shift to, yeah, the equilibrium will be shift to the left. Which means what? What happens to the product concentration then? Yield of the ammonia, yield of the phosphate will be decreased, which means the concentration PO4 3 minus will be decreased. Therefore, it is hard to form the precipitate in the acidic environment for the phosphate. Okay, I'm using a bit of the module 5 and mix that with the module 8 in here. Again, something we did in the module 7 about ester, that dehydrating agent, something, yes, why we need to use the sulfuric acid in the esterification, because they are dehydrating on your product side. Therefore, we can increase the yield of the product. I'm saying module 5 can be mixed in anywhere, anytime, like this. So guys, just think about like just try to construct the formula, like equilibrium formula like this. It will help you to answer the question better. Now, does it make sense to you? Good. Do you understand that point now? Good. All right. Could you guys try to do question 3, devise a method question? Yeah, colorimetry, that's next week. Unknown test tube is thought to contain either sodium acetate, sodium hydroxide, and sodium sulfate. Okay, devise a method to identify the contents of the test tube. So method means that you need to be very, very, very specific. So you say start from this. You should start from take a sample of the solution. So Jiang, we have acetate, hydroxide, and sulfate. What would be your first method? What cation would you use? Acetate, hydroxide, sulfate.
뭐요? 나 했는데요.
Okay, if you do that, okay, you can get the sodium and hydroxide, acetate. Okay, yeah. What litmus, red or blue? Okay, use red litmus paper. Okay, to observe any color change. Good. Then, if the litmus turns into from red to blue, it's either, turns into if there is no color change, in litmus, then it must be if no color change in the litmus paper, the blues from red to blue, no color change, it must be the solution should be sodium sulfate. Why? Because sodium sulfate is only one that doesn't change the color. Okay. Now, if the litmus turns to from red to blue, then what we do? So it means that it must be the hydroxide or the acetate. So how do we differentiate them?
Use dilute H and agree.
Yeah, and
If there's bubbles,
Ah.
No. If there's wait, no,
No,
you
No.
use CuNO3.
so we put some, add some, about 2 mil. We can identify the volume, but you can say add some copper nitrate, okay? And what do you expect for the copper? With blue precipitate, with if the blue precipitate present means that there is a sodium hydroxide. Good. There's a no precipitate. It is the acetate. Very good. So divisor method means, yes, we need to think about like how you're going to construct the actual methods like this. Okay. All right. So same things here. I would like to try the question on your page 35. Let's try yourself question 2. Could you guys try to do this question now, please? By the way, this is very similar to the one of the HSC questions, practice questions we used to have. Okay, so for the barium, lead 2, and the copper 2. So, Mina, what would be your first step? You add some, okay, add sodium hydroxide, then what do you expect? Okay, color, no precipitate, white. Okay, color precipitate, which is blue. Okay, that's a copper. No precipitate.
There's like enough concentration.
There's no. Okay.
Like a high enough concentration. It's calcium. It's what? No, I did the wrong thing. I did calcium.
Hydroxide would not form anything with the barium.
Yeah.
I will do something with the. Does it do something with the lead? With the brown? It's white. So that'll be the no, it's okay. White precipitate would be the lead. No precipitate. Any precipitate with the barium, with the hydroxide? No, that the barium. Okay, that's one process we can do. Any other methods, Jim? How about we start with the okay, let's try the 3 methods we learned from here. What about adding some HCl? The white precipitate, okay. White precipitate, that means it must be lead 2+, okay, no precipitate. Then, what is the second step? Add ammonia, okay, let's add ammonia, NH, dilute. Then what do you expect for the calcium and the barium? No precipitate for both? Then what's the point? What about sulfate? Barium sulfate? Yeah, we can add some. This is what I mean. You don't always need to follow the flow chart. You have to think about the precipitation of the barium and the calcium. Okay, add sulfate means that we get the white precipitate. This must be the barium 2+, no precipitate. That must be the calcium. We can test that with the either with the fluoride or either with the flame test if you like to identify whether that's a calcium or not. Oh, sorry, copper. Why am I keep copper? Okay, now here's one thing. The question here is telling you, hey, we have some solutions of this separately. This is very important, Mina. We have separated flask of this. But what if we have mix of this? And then questions asking you, I want you to separate them. I want you to separate them. Can we use the first method to separate this barium, lead, and the copper?
From the one solution.
Yeah, from one solution, one flask, we have mixed up the barium, lead, and copper. Can we separate them using the sodium hydroxide? No. What the problem is, yes, we can identify which is which by using the sodium hydroxide there, but we can't separate them because it will be mixed up the all blue and white and no precipitate. So it will be like some mix of the blue and white. Means we can't separate them. Means that we need to use this method. So first of all, adding some hydrochloric acid as the lead will only reacting, only make a precipitate with the chloride, we get the white precipitate. What you do, you filtrate this. Okay, once you filtrate the white precipitate with the using a filter paper, we know that in the remaining solution, that will be the mix of the barium, and copper. Then adding some sulfuric acid, we also get the white precipitate again, UV filtrator again. The rest we have in the copper. If you want, the question's asking you to identify what that is, confirm that, you can use the flame test or the fluoride to see whether there's precipitation or the colors or the blue color in the flame test. Okay, read the question very carefully, because the question can be, the way you need to answer the question can be deferred by that question. Most of the times, yes, you're given questions like this, but sometimes you get a question like, hey, we want to separate it. We want to separate it. And in that case, you need to use a different method like that. Okay, any questions about question 2? All right, I'll leave the rest of the questions for your homework for next week. And we can try some HSC and some sample question once you come in. All right, 16. Yeah, let's finish now today. All right, that's it.